Hello, my name is Sophia Abshire and I am in 6th grade, and my experiment is sodas are cool. And my abstract for this experiment is if it's ever on a really hot summer day and you really want a cool soda. My hypothesis is soda will cool the fastest in an ice water bath. Some of the ways that I controlled the variables where I covered each soda to avoid evaporation. Cooling devices were opened only to check soda temperatures to ensure outside air did not have any effect on the sodas or the cooling devices. The thermometer was wiped clean before inserting it into the next soda to avoid any change. The real question here was, what's the quickest way to cool a soda? A refrigerator, an ice water bath, a freezer, or a tub of ice? My procedure was I checked the temperature of the room first, and it was 68 degrees Fahrenheit. Then I checked the temperature of each cooling device in Fahrenheit. Refrigerator 39 degrees, the freezer was below 32 degrees, the ice was also below 32 degrees, and the ice water was 34 degrees. I opened each can and checked the original temperatures of the soda. All 12 were 68 degrees Fahrenheit, which was the same as the temperature of the room. I placed plastic wrap and ponytail holders to keep the plastic wrap on top of each can. I put 3 in the freezer, 3 in the fridge, 3 in the ice, and 3 in the ice water. And my materials used here were all of these, if you want to take a look. And my results were approximately 15 to 20 minutes from the beginning of the experiment, all measurements in Fahrenheit. The data below is an average of the 3 sodas in each cooling device. Ice water, 34 degrees, freezer, 46 degrees, ice, 48 degrees, and fridge, 60 degrees. And as you can see in my graph below, the refrigerator was definitely the slowest to get cold. And the ice water was definitely the fastest, but at the end, the freezer caught up with it a little bit. But the ice is very inconsistent, so it kept going up and down. And my conclusion was that my hypothesis was right, that the soda would cool fastest in an ice water bath. The reason that this cooled the fastest was because it used convection. Conduction is a transfer of heat that uses touch. For example, if you touch something really, really cold, then you'll get cold too. And the fridge and the freezer used convection, which is the transfer of heat through a liquid or gas by currents. Example, the refrigerator or the freezer, like I was talking about. And my research was 4 different ways to transfer heat or cool things in this experiment. I observed conduction and convection. I did not use the other 2. In the coolers, conduction is observed. The refrigerator and the freezers use convection to cool sodas. The dictionary defines convection as heat transfer by upward movement of a heated and less dense medium. Simply stated, the circulation of heated and cooled air creating a current. The molecules in ice water mixture are something in freezing cold ice water. It will get cold faster than it were surrounded by air. And something else I learned in this experiment was I learned more about temperature, which is that cold molecules vibrate slower and hot molecules vibrate faster. And this is my bibliography if you want to take a look at what I used to research and learn more about this experiment. Again, my name is Sophia Abshire, and something I want to tell you, I spilled my soda on the floor and it was so depressing. And this is my experiment.
Hi, my name is Sophie Gossen, and this is my project, I Saw the Light. I was researching about robots, and I found one controlled by a light sensor, also called a photoresistor. Photoresistors are used in cell phones and tablets, which can adjust their screen brightness to how bright the room is around them. My question was, how does the brightness percentage of environmental light impact the response of a robot controlled by a light sensor? My hypothesis was the higher the percentage of environmental light brightness, the less likely the robot will respond to only directional light. My materials are basically just the Bluebot robot, flashlight, GD light bulbs, tree lamp, and other measuring items. For my procedures, pretty much just build the robot, measure everything, and put tape around it so the experiment can be repeated, and find the highest percentage of environmental light brightness without a response and the lowest percentage of environmental brightness with a response. The first time the robot responded to environmental light brightness was at 75% brightness. And then I tested 1% on either side of that, 75%, to find out that 74% the robot never responded to environmental light, 75% the robot sometimes responded to environmental light, and 76% the robot always responded to environmental light. I think the results supported my hypothesis, and that this experiment is important because if robots are going to be using light sensors, people are going to need to know what environmental light brightness they're most effective in. Thank you.
Hi, my name is Willow, Shank, and I'll be presenting on dry ice. So last year I went to a vacation Bible school, and their theme was Pirate Island. So they decorated with this big volcano, and it had smoke coming out of it, and it lasted the whole week of VBS. So I learned that dry ice, when it's added to liquids, can create this fog effect. So I wondered, what happens when dry ice is added to different liquids? Does it affect the character of cloud produced or the duration of fog production? So I researched a little more on dry ice and found out that it is the solid form of CO2, or of carbon dioxide, and it freezes and becomes a solid at negative 109 degrees. So that is very, very cold. And something that makes it really unique is that it transitions directly from a solid to a gas without hitting a liquid state in between. That process is called sublimation. So that's a word I'm going to be using a lot, so you might want to pay attention to that. So, and I did find out that it increases that it interacts with the liquids in different ways. So here's more about the liquids now. The liquids increase the temperature of the dry ice, and that speeds up the sublimation process. So to understand my experiment, I first had to understand what surface tension was. So surface tension is a measurement of how tightly the bond of molecules are. So liquids with high surface tension, so a liquid with a high surface tension would mean that if, like for example, if you had a water dropper and you dropped a little drop of liquid onto a non-absorbent surface, it would generally stay in that like drop shape. So that is because of surface tension. So with high surface tension, it makes a slower sublimation. So it causes a single bubble to form around the dry ice when the dry ice is dropped in, which is pretty cool. And so that bubble around it insulates the dry ice from the warmth of the liquid. And so there's no direct contact between the dry ice and the liquid. That makes for a slower energy transfer. With low surface tension, however, it makes a faster sublimation. So instead of one big bubble forming around the dry ice, it makes a bunch of little tiny bubbles form on the dry ice. So that doesn't really do anything to insulate it. So there is direct contact between the dry ice and the liquid, which makes for a rapid energy transfer. So the 4 liquids that I tested the dry ice in was water, ethanol, acetone, and glycerol. I chose water and glycerol because those two both had a high surface tension, and ethanol and acetone because those two had a low surface tension. So I wanted to see the varieties of surface tension. So my hypothesis was that dry ice added to different liquids will create different outcomes, and that water will produce the thickest fog for the longest amount of time. So here's some risks that I could have encountered and some safety precautions to go with them. So one was not being able to get dry ice. So I had to plan to do my experiment early because the store that carries dry ice was out of it frequently. So if one day I couldn't get it, then I could always go back like the next week and try to do my experiment again. Another risk was the dry ice sublimating before the experiment is complete. So to avoid that, I had to purchase the dry ice the day of the experiment and use a cooler to transport and store the dry ice. Another risk was inhalation of dangerous compounds, and so I had to leave the vehicle windows open when we were transporting the dry ice, because dry ice is CO2, and so that's what we breathe out, not what we breathe in. So if a room fills up with too much CO2, it can get hard to breathe. So I also had to keep the room well ventilated, and I also could not purposely inhale two of my liquids, ethanol and acetone, because they could be dangerous if you inhale them. Another risk was an explosion. So the dry ice could make a pressure buildup if it was in a sealed container. So I had to leave my cooler lid open when I was transporting it. Another risk was frostbite. So dry ice is negative 109 degrees. So if you touched it, you would get frostbite like that. So I had to wear a long sleeve shirt, gloves, pants, and safety goggles. And one more risk was a fire. So ethanol and acetone were both flammable, so I had to not expose them to a flame. My materials were dry ice, water, ethanol, acetone, glycerol, and then I needed my beakers, heavy-duty gloves, a cooler, a timer, and tongs. My procedure was I purchased the dry ice the day of the experiment, and then I chose a location. I set my 4 beakers out about a foot apart, and I filled them with 150 milliliters of each liquid. Then I let them sit for like 3 hours just to make sure that they were all starting at the same temperature. Then I so the dry ice comes in a big block, and so I obviously couldn't fit that in a beaker, so I had to break it into 4 different chunks, and then I weighed them with the kitchen scale to make sure that they were like the same weight. And then I dropped each of my 4 pieces of dry ice into each of my beakers. Then as soon as I did that, I had an assistant start a timer, and then I recorded the length of time that the fog lasts and the duration of fog production. So according to my experiments, the ideal fog producing liquid was water. This experiment was completed twice, both times showing very similar results. So water's fog was thick, constant, overflowing, and it was kind of springy. And it lasted for 456 seconds, which was about 7.5 minutes. Then acetone's fog was wispy and thin, and it only lasted 20 seconds. And then ethanol, its fog was thick but not overflowing. And that one only lasted 186 seconds, which was about 3 minutes. And glycerol actually produced no fog at all. So my conclusion was that my original hypothesis stated that dry ice added to different liquids will create different outcomes, and that water will produce the thickest fog for the longest amount of time. My data shows that my hypothesis is true because the dry ice that was added to water created the most fog for the longest amount of time. This is the end of my presentation.
My name is Jonah and I am in 7th grade. My title is Persnickety Chocolate Science. Chocolate is delicious. It can be sweet, salty, or even in between, and it can also have a delicious filling. I enjoy eating chocolate and am interested in the science of tempering. I wondered if varying cocoa percentages temper the same or better than 70% chocolate. My hypothesis is that the higher the cocoa percentage, the harder the chocolate will be to temper. The question that I answered is whether or not the percentage or amount of cocoa in dark chocolate affects how it is tempered. For my background research, I researched how chocolate is made and the science behind tempering. When chocolate is tempered, it will have an appealing, smooth, shiny surface and a clean snap when broken. Tempering is when chocolate is slowly heated and cooled at a specific temperature, which vary according to the type of chocolate. If chocolate is not tempered correctly, it will have a bumpy and dull appearance with white streaks spattered throughout the chocolate. This is because the cocoa butter inside the chocolate did not crystallize the right way. Tempering is a way to manipulate chocolate, and if done correctly, it will give it a professional glossy look. But what is the science behind tempering? When chocolate is melted, the fatty acid crystals inside separate. Tempering brings the crystals back together to form a solid mass. Cooling the melted chocolate forms nuclei around the fatty acids, and fatty acids in turn crystallize around the nuclei. Then raising the temperature ensures that the crystals do not turn solid. Heating and cooling temperatures vary with the type of chocolate. Milk chocolate has extra milk fat, which requires a low melting temperature. Dark chocolate, on the other hand, does not contain extra milk fat, so it needs a higher temperature to melt. My materials are 3.5-ounce bars of Lindt X-Link 70, 85, and 90% cocoa, a cutting board, a chef's knife, a canning thermometer or an instant read, a medium glass bowl, a spatula, pot, water, and a polystyrene mold. What I did for my procedure was first I cleaned and dried my tools. Then I took the chocolate out of the packaging and separated 20% and 80% of the chocolate. Then I chopped the 80% evenly and finely. Then I poured 2 cups of cold water after testing and recording the temperature into a medium-sized pot. Then I poured the chocolate into a bowl, put the bowl on top of the pot, and the pot on top of a burner. Then I made sure the bowl does not touch the bottom of the water and turned the burner on medium. When the chocolate began melting, I stirred it with a spatula. Then I put the thermometer in the chocolate. When the water began to simmer, I turned it down to medium-low, the temperature. And while the 80% chocolate was melting, I chopped the rest of the chocolate, the 20%, evenly and finely. But I had to be careful because if the temperature goes above 130 degrees, it will burn. Then once the melted chocolate reached the temperature of 120 degrees Fahrenheit, I immediately removed the bowl from the heat and began adding the remaining 20% chocolate 1/3 at a time, waiting for each third to melt before adding the rest. Once the chocolate cools to 82 degrees Fahrenheit, I put the bowl of chocolate back on the top of the pot of boiling water. Then I brought the chocolate temperature up to 120 degrees and poured the chocolate into the molds immediately once it reached that temperature. Regarding risk and safety, while moving the pot, I could have burned myself, so I made sure to wear oven mitts. And like I said, I had to be careful that the chocolate did not go above 130 degrees Fahrenheit, or the chocolate would burn. For this experiment, I will be testing the spontaneous snappiness of the chocolate with a decibel app called Decibel Meter, and grading the machine with a rubric, taking pictures of the chocolate. Lastly, I will test the melting properties by placing the tempered chocolate in a 125-degree oven and timing how long it takes before it goes from bar to puddle. As I performed the experiment, I recorded the time and temperature when the chocolate was heated, cooled, and heated again. My experiment overall went well, but occasionally the chocolate temperature would go like a little bit above, and I did do 3 trials of each bar of chocolate. And then for my log, I charted I charted everything that happened in here, and I also put the rest of my research paper and everything else. To record the data, I created charts for each of the percentages of cocoa for the decibel snap test. I averaged the results of all 3 tests to find the overall decibel average. I tested the snap of each chocolate bar using a decibel meter app. Using a quiet room, I snapped 3 portions of each bar 5 inches away from the phone while recording the screen during the decibel app testing. Then I looked back at the recording and slowly scrolled through the video to chart the highest number which occurred during the snap. For the sheen of the chocolate, I made a rubric to record the level of shine for each percentage of all 3 tests. Lastly, I created a small chart to record the data for the chocolate melting test. Using a cookie sheet, I placed a single square of each chocolate percentage onto the sheet. Then I set the oven to 125 degrees, placed the chocolate inside the oven, and timed how long the chocolate took to melt into a puddle. The results of my experiment show that although 85% chocolate bar had the highest decibel snap average, which was a 59 decibel, the 90% had the chocolate melted the fastest and had the best shine, which are the essential properties of well-tempered chocolate. 90% had the second highest decibel snap average. Sheen was graded with a 4 and came in first for the melting test. The 70% had the lowest snap average in decibel testing. The Sheen was graded with a 3 and came in second during the melting test. 85%, although it had the highest decibel snap average, came in last in the melting test, and Sheen was graded with a 2. Since 70% chocolate tempered the worst and 90% best, these results disprove my hypothesis, which was the higher the percentage of cocoa, the harder it will be to temper. Therefore, each percentage of chocolate needs a specific recipe with different temperatures for heating, cooling, and reheating in order to obtain an excellent temper. Interesting studies for the future would be to test different brands of a single percentage of dark chocolate, or to compare the ingredients of different brands of chocolate to discover which brand tempers best. Food scientists and chocolatiers may have to invent or use new recipes for each percentage and experiment to see which recipe is superior. The 85% bar shine was the worst, and looking at the ingredients, 85% has less fat. Fat makes things softer, and less fat may have caused the 85% to have the best snap. Therefore, each percentage of chocolate needs a specific recipe with different temperatures for heating, cooling, and reheating in order to obtain an excellent temper.